All right, let's pull back the curtain on the silent, tireless engine that makes your entire digital life possible. We're talking about the operating system. I mean, think about it. You're writing an email, you've got music streaming in the background, a notification from your calendar pops up, and maybe you're downloading a huge file all at the same time. How does your device not just give up? What's conducting this whole complex orchestra?
Well, the answer is the operating system, or the OS. You can think of it as the government, the traffic cop, and the resource manager for your computer, all rolled into one. It's the absolute foundational piece of software that everything else runs on top of.
But, it wasn't always this good at juggling. The story of the OS is really a story about this relentless quest for efficiency. It all started with computers that could, believe it or not, only think about one single thing at a time.
Way back in the day, we had what were called batch systems. A computer would run job A until it was completely finished, and only then would it start job B. Super inefficient. Then came this clever trick called multi-programming. The idea was, if job A is busy waiting for something, like a file to load from a slow disk, the OS would switch over to job B to keep the processor from just sitting there doing nothing. And this idea eventually leads us to modern multitasking. Here, the OS doesn't even wait for a job to pause. It actively switches between all of them thousands of times a second, giving each one a tiny slice of its attention. And that's what creates this perfect illusion that everything is running at once.
And this is where it gets really interesting, because it reveals this fascinating shift in philosophy. The goal of multiprogramming was all about the machine. Don't waste a single CPU cycle, keep it busy. But time sharing? That's all about you, the user. The goal is to switch tasks so fast that your experience feels smooth and responsive, even if it means the CPU isn't being 100% efficient. It's really the difference between designing an efficient factory and creating a great user experience.
So making one processor work smarter was a huge step, but eventually we just hit a physical wall. To get more power, we needed a totally new approach. We needed more brains on the job.
And that brings us to multiprocessing. The idea is actually pretty simple. If one central processing unit, a CPU, isn't enough, hey, let's just add more. 2, 4, 8, even 16 of them. Think of it like having multiple chefs in a kitchen instead of just one. Now tasks can happen in true parallel, not just being switched back and forth really quickly. It's just a massive leap in raw, brute force power.
So what's the next logical step after you stuff multiple processors into one box? Well, you start connecting multiple boxes together. In a network or a distributed system, you link up a whole bunch of separate computers so they can share tasks and data. I mean, the entire internet, cloud computing, that's all just giant distributed systems built on this very idea.
Okay, so we've talked about OSs that are efficient and OSs that are powerful. But what about the ones that have to be, well, punctual? Because in some fields, timing isn't just important, it is literally everything.
This quote just nails the whole concept. Just imagine the computer that controls a car's airbags. If it does the calculation and deploys those airbags even a fraction of a second too late, the result is catastrophic. The answer can't just be correct, it has to be correct right now.
And this is the world of the real-time OS, or RTOS. You find these in places where failure is just not an option. We're talking aircraft control systems, medical pacemakers, the robots on a factory assembly line. For these systems, being predictably on time is way more important than being lightning fast.
This chart just lays out the different priorities so perfectly. A batch system? It just wants to chew through data, no user in sight, and response time could be hours. A time-sharing system, like the one on your laptop, is obsessed with making your interactions feel instant, within seconds. And a real-time system? It is a total slave to the clock, where responses have to be measured in thousandths of a second.
Okay, so let's bring all of this home. How do all these historical ideas and different types of operating systems actually show up in the device you're probably holding in your hand right now?
Well, the magic happens through something called system calls. See, an app on your phone can't just decide to access your camera or save a file all by itself. No way. It has to ask the OS for permission first. And these requests, these system calls, are like the universal language for getting things done safely and securely.
And what's so amazing is that this entire history we've been talking about is playing out in your pocket this very second. When you swipe between apps on your phone, that is the magic of multitasking. The reason your game looks so incredibly smooth? That's multiprocessing thanks to your phone's multi-core chip. Sharing a photo over Wi-Fi? You're using its network OS features. And that little pop-up that says, "Can this app use your camera?" That is a system call, making sure your privacy is protected. So, from its humble beginnings as just a simple job scheduler to the incredibly complex, powerful manager that lives in your pocket, the operating system is truly the unsung hero of it all. It's the invisible engine driving our entire digital world.
And that kind of leaves us with a final thought to chew on. Today's operating systems are built for clicks and taps on a screen. But as we move toward a future full of smart homes and connected cars and augmented reality glasses, what new problems will the next generation of operating systems need to solve? What is that unseen engine going to look like then?